Let me now discuss the forward converter with demagnetizing winding where the core reset is lossless. We have been discussing forward converter where the core reset was lossy, wherein we had put a diode resistor combination across the primary and the magnetization energy was lost in the resistor as heat. Now in this configuration, we have removed the diode resistor combination for core reset, and we have introduced a third winding called the demagnetizing winding with opposite dot polarity, such that when this switch turns off, you will see that the non-dot end will become positive and will drive the magnetizing current through this demagnetizing winding, forward biasing this diode D. So this way the core reset will happen, but note that the magnetizing energy is pumped into the supply, thereby recharging the supply, and it is not getting lost as heat, and therefore the efficiency of this type of core reset forward converter is much more because it is lossless. All other aspects of this forward converter is the same as we have discussed previously. We will simulate this and try to understand how this lossless core reset happens. Before that, there is this component which is forward transformer component. You can find it in the components dialog. I will open this ACOMS, and if you scroll down, you will see that there is a forward transformer symbol and model which we can use for this particular circuit. So this is having the model of the forward transformer, and when you double click on that, you will see that it is a sub-circuit XFM4. We have given a NP 10 turns, ND which is the demagnetizing winding, the central winding here 10 turns. We have made that same as NP. NS is 20 turns, and see the permeance is 150. So this is the parameters that we are passing into this forward converter transformer model. Now the sub-circuit model for this is placed in edt01.sub. I will just show you now. So when I double click on this sub-circuit file, you see that there is a list of sub-circuits. We go down, scroll down, and below the gyrator model, I have here the forward converters transformer XFM4, and the default parameters which are kept here is NP is 1, ND 1, NS 1, and this one, but we have given different values of the primary and the secondary turns, the demagnetizing turns. It has 3 gyrators because there are 3 windings. Each winding is associated with a gyrator, and we are passing the parameters, which is the number of turns. And the gyrator model is the same as the one which we discussed for the normal transformer in the lossy forward converter. So now you can see what is there in the .cir file. Same as in the earlier forward converter transformer, 10 milliseconds is the simulation time, including the netlist, and as before, background is light and the foreground is dark, and I'm plotting the output voltage, the inductor current, and the secondary current of the forward converter transformer. Let us simulate and then check. We will open this command window, and we are already in the directory of the lossless forward converter. Before that, I would like to show that I had earlier written this file runsim, which is an executable file, and here the netlist I have put it as a statement, a script statement in Octave, and I am passing as arguments the whatever the file, schematic file and the netlist file that I would like to have. So I am entering the schematic file and the netlist file will come as the output, and then immediately after that I am calling ngSpice and with the same argument the .cir file. So it will make my I don't have to type the netlist generation command every time. So I will just call this run sim. So this is what I would be doing now. So in the forward converter I will call that run sim forward. So it will, what this command will do is it will take forward.schematic and regenerate forward.net, and then later call ngSpice through this forward.cir. So this is what it will do. Let me run the simulation. See that netlist has been generated, simulation has run, and the display of the results as evident on the screen, very similar to the regular forward converter with the lossy flux reset. We saw this also. Similar waveforms. You can of course view every node voltage and different branch currents and understand this circuit too, but I am interested to see and compare the demagnetization, that is core reset, flux reset, and the currents through the demagnetizing winding, and compare it with the lossy core reset forward converter. Let us now check the current flow in the primary of the transformer flowing through the switch by measuring the current of VIQ, zero source voltage, and also we will see what is the demagnetizing current that is flowing through the diode when the switch is off. So we can plot VQ and VIQ and VID. So this will give you the let me just see couple of cycles here, 2 or 3 cycles, so that it is clear. So you see that this red waveform is VQ, it is the voltage across the switch. So this is the voltage across the switch when it is off. When it is on, it is just the on state drop across the switch. And when it is on, this blue waveform is the current through the switch, and it is also the primary current through the switch. The IVID, which is the demagnetizing current, it is very small. It is not, we are not able to see that here. Let me zoom this. See, it is going to happen when the switch is off. So let me zoom this around this point, and you will see the triangular wave shape where it linearly falls down to 0 and resets the core, because this is only the magnetizing current compared to the load current which you would see in the primary. This is a very small quantity. This is in milliamps. So you see that demagnetizing is happening during this time. Probably it will be very clear if we just only see the demagnetizing current waveform. So what I will do, I will just plot IVID. This is the demagnetizing current. So you will see that this is a sequence of falling linear triangular waveform. This is the magnetizing current which linearly falls down to 0, because a constant voltage is applied across the demagnetizing winding, as the demagnetizing winding is pumping this energy, this current into the supply. So this is happening during the time when the switch is off. So let us probably compare this with the lossy forward converter circuit where it was exponential, so that it will give some insight into that. So let me close this. I have on the screen now both the forward converters. On the left side you have the lossy forward converter with the diode resistor combination across the primary. On the right side I have the forward converter with the lossless core reset, where you have the demagnetizing winding in between here, which leads to lossless core flux reset. So let us see the plots of the demagnetizing current IVID in both the cases. So this is the demagnetizing current of, let me take a very small portion so that we will be able to see the exponential fall of the demagnetizing winding, and this is mainly due to the L by R time constant in this freewheeling path. Likewise, if you plot IVID for the lossless converter, I will zoom in to only a few. Yes. So here you see that because the voltage across the demagnetizing winding is constant, the LdI by dt, di by dt, I will be a linear fall, because the flux N d phi by dt, phi is also a linear fall. So here you see that in a fixed amount of time the core will reset, as we have seen in the theory and theoretical waveform. So both these waveforms can be validated in this way in simulation and corroborated with the theory that we have learned. Likewise, I recommend that you try to compare the voltages across the primary, voltages across the switch in both the circuits, and trying to gain more insight into both of these circuits.